Hey, good afternoon, everyone. My name is Seth Hamblin. I appreciate everyone joining us today for what we hope are what we're looking forward to is a couple of really excellent and informative case studies. If you found us, you know that this is the DFI Driven Pile Committee webinar series. This is our impact webinar series that we've been hosting for the last 2 years. This beginning of 2025 will be our 3 year, the start of our third year. We're very proud of the content that we've been able to create and bring to our membership and bring to the committee. And, we're looking forward to continuing that with today's presentation. For those of you not familiar with this webinar series, we're hopeful that we have some new folks here. No, the intent of this programming is to highlight innovative developments, case studies and current practices within the deep foundation and specifically the driven pile industry. That includes what we're going to talk about today, which relates to marine foundations and marine and waterfront structures. It's the first time we've addressed this topic in our series. And given that our committee merged several years ago with the Marine Foundations Committee, we're hopeful that this content helps drive some new interest from the folks that maybe work in the marine and waterfront sector a little more. Get a little background on our webinar series. In the past, we've discussed things like ductile iron pipe and new trends in pile driving, vibratory hammer products and applications, innovative pile materials, specific design concerns like down drag and its effect on driven piles. Talked about case studies with large diameter open-ended pipes. So try to really get a wide breadth of information when it comes to driven piles. And so we're hopeful that the presentations by our speakers today are going to add to that repertoire and really help continue us in providing the content that our members are looking for. So just a couple of housekeeping items before we get started. We appreciate that if everyone in the audience keeps their mics on mute, that would be a big help to our speakers. We will have a Q&A at the end. And if you want to ask questions, please use the chat feature and put your questions in there. And then when we get to the end, we'll go through that list and get some insight from our speakers. So our speakers today are shown here on the screen. We're going to start with the two gentlemen from GZA Geoenvironmental. With us today, we have James Marsland and Greg Dimillio, both out of the Providence office of GZA. They're going to be speaking to us about a really interesting job took place in the south coast of Connecticut. It's the State Pier complex, and their presentation is entitled Placing and Compacting 400,000 cubic yards of fill in the Thames River for the redevelopment of the Connecticut State Pier complex. And with that, I will turn it over to them.
Thanks, Seth. Hi, everyone. I'm Jim Marsland from GZA Providence. And today, like Seth said, we're going to be talking about the State Pier infrastructure improvement projects in New London, Connecticut. Next slide, please. So an overview of the project. This is the first purpose-built marine terminal for offshore wind. And essentially, it's, like I said, it's purpose-built to accommodate offshore wind components, specifically the tower sections, the nacelles, or the turbines, and blades. It's located in New London, Connecticut, on the south coast of Connecticut, and it's in relatively close proximity to a lot of the offshore wind lease areas of the coast of the Northeast. Next slide, please. So the existing State Pier complex consisted of two adjacent piers, and the objective of the project was essentially to connect those piers to create a 16-acre solid fill wharf. The wharf is designed with a relatively high bearing pressure, 3,000 PSF capacity, and there's a couple of heavy lift areas that are at 5,000 PSF capacity. Dredging was involved in the project for deep water berths, specifically for jackup vessels and offshore wind turbine installation vessels. there's, in addition to just offshore wind, there are some long-term benefits to the port facility just by increasing capability. The project was substantially complete in the spring of 2023. Next slide, please. So the project team, Connecticut Port Authority was obviously involved. The project was led by the joint venture between Ørsted and Eversource, who are building offshore wind farms right now. The design team was led by Moffett and Nickel with support from Haley and Aldrich and AECOM. The general contractor and the construction manager at risk was Kiewit, and GZA, our team, worked for the contractor, which gave us a unique opportunity for the delegated design of the infill between the two piers. Next slide, please. So Central Wharf is what we call the area between the two piers. This is approximately 8 acres of water. Water depth was about 40 feet. Filling Central Wharf would have required 400,000 cubic yards of fill. And doing this, there's really 3 main challenges. There's a very thin layer of organic silt on the bottom. It's very soft plastic material. And there's fear that if you place fill over this material, it will mobilize, it will mud wave. You'll actually push it out of this basin and into the river, which we could not allow to happen. So that was challenge number 1. How do we immobilize that organic silt? Dredging and removal of that material was really cost prohibitive. So how do we keep it in place, mobilize it, stabilize it, bury it? Challenge number 2 was we had to place 40 feet of fill through 40 feet of water, which is obviously has some challenges associated with it. And then finally there's a closure wall, there's a combi wall, pipe Z wall that connects the two piers. And that wall is anchored, it has a dead man system. So how do we sequence the construction of that dead man system with the placement and densification of the fill? And that presented some challenges. It was basically a big geometry problem that we kind of had to figure out as we went along. So next slide, please. In addition to those 3 challenges, as I mentioned, there's some performance requirements for the Central Wharf and really the entire wharf. Again, 3,000 PSF bearing pressure, 5,000 PSF heavy lift areas. There's long-term settlement, time-dependent settlement tolerances that we had to meet. We had to mitigate liquefaction, make sure we weren't going to have a liquefaction problem after this fill was placed through the water. And we also had to densify the fill to meet the bearing capacity requirements. Next slide, please. So I guess to go back to those 3 main problems, the solutions that we worked with the contractor to develop and implement here was, in terms of immobilizing that organic silt layer, we devised a plan consisting of what we called moguls, basically sand piles that were strategically placed along the bottom of Central Wharf. And the idea was to penetrate that layer of organic silt and essentially create mounds that would prevent a mud wave from occurring as fill was placed over the top of them. And then in terms of the placement of the fill, it was simply end dump and push into the water. But then in terms of densification, we developed a couple of different methods of densification to deal with that, consisting of vibro replacement of vibro compaction that was done from a dry working grade. And then again, we addressed the sequence issues to allow the placement and densification of fill and the construction of the dead man system. Basically, just like I said, working through the geometry of what our fill slope through water looked like, and how the compaction was progressing, so that we could get that pile supported dead man installed. Next slide, please. So with that, I'm going to turn it over to Greg Dimillio, who's going to talk about the construction of the Central Wharf infill.
Thanks, Jim. So to discuss the construction, how we actually did this, we're going to show how we constructed those moguls, got those installed into the basin, how the mass fill procedures were moved along, how we actually densified the fill, and then what went into the relocation of that dead man system. Next slide, please. So just to give an overview of what we were working with. So in yellow here, that's that soft layer of organic silt that Jim mentioned. As you can see, up in the north, in the shallower end of that basin, there was a much thicker layer, but generally there was a thin layer that covered the entire bottom of that central wharf. In red, this would be the idealized profile once all that fill was placed. And then below the organics, that's where you have your natural silty sand layer. Next slide, please. So when it came to placing the moguls, we wanted to immobilize the organics across the entire basin. So the moguls were strategically laid out to cover that area. We wanted to do it efficiently, so they were spaced approximately 40 feet apart. At the same time, the intent of these moguls was to prevent any mobilized organics, should they be mobilized, to not have a clear path all the way out of the basin. So they were arranged in the rough pattern that you're seeing on the screen in a staggered manner throughout the entire basin. Next slide, please. So to actually get these moguls or sand piles into the water, a few different pieces of equipment were utilized. The first piece of equipment, that was a material handler that had a clamshell bucket. This piece of equipment was on a barge, which was able to move around the basin. And the way this actually installed the moguls was it physically picked up that granular material and it was able to place it all the way at the bottom in a one like localized group. And additionally, we also used a crane with a very similar clamshell attachment that moved around the basin, similar to the material handler, and these pieces of equipment were operating simultaneously. The third piece of equipment that was utilized was a telebelt. A telebelt is like a telescoping conveyor belt that's able to rotate circularly and also change its radius at the same time. So granular fill was fed into the conveyor belt and then it was transported into the water column vertically as opposed to being placed directly at the mud line, like the other pieces of equipment. Next slide, please. So as the moguls are being placed, all the pieces of equipment are working, we needed a way to verify that what we intended the moguls to do was actually happening. Now, when you're working in water that can be up to 20 to 40 feet, there's really no way to visually observe what is actually happening at that mud line, how you would any other construction project. So we needed a way to actually know that these moguls were not just flattening out, we're not getting absorbed by the organics. So we used a couple of different methods to try and visualize these moguls. The first method we tried to use underwater submersible cameras. It didn't work as efficiently as we had hoped. That was due to visibility concerns and just the overall size of the basin. We tried localized soundings. The problem with that is you had to be very exact to know that you were on a mogul. So ultimately, we determined that using a bathymetric survey gave us a very clear and wide picture of what was happening at the bottom of that central wharf. So this is actually one of the first bathymetric surveys we took after the moguls were being installed. And what you can see is all the localized raises in that mud line when compared to the baseline survey. So that gave us an idea that the moguls were actually holding their shape and rising above that mud line. Next slide, please. So once the moguls were in place, that was our method of immobilizing the organics. The next step was to begin the mass fill process. So this was done with end dump with the fill and then pushing it into the basin. And overall, there was 400,000 cubic yards that were required. So this procedure, it was repetitive, but it kept going and it moved down the basin. To source all this, there was both on and off-site sources just to acquire the proper volume. And as the filling progressed down, we needed to be mindful of the sequence that would need to occur to construct that combi wall and dead man system. Next slide, please. So we knew that the fill that's being placed needed to be densified. So in order to make sure that what you're placing is going to be densified effectively, you got to make sure that there's some controls on what material you're actually placing. Now, for this project, there's about 20% that was sourced from cuts of upland on-site material, and about 80% that were sourced from off-site sources. To effectively control what the material is, we used FHWA guidance that would identify what an effective gradation would be for densification of fill underwater. So this graphic on the screen, this is showing those FHWA zones based on the gradation. According to their guidance, zone B was the ideal zone for this. And as you can see, the sieve results of the material that we used roughly fell into this zone. Next slide. So similar to the moguls, we needed a way to verify what was actually happening underwater. We tried soundings. The issue with that is you don't get as much coverage as you can with the bathymetric survey. So we decided to do periodic surveys to get an idea of what was happening as this fill was going in. Now, that main challenge, number one, that Jim had mentioned, that was immobilizing the organics. So one of the key things that we were able to determine from this is there was not a uniform raise in that mud line that would be indicative of all this soft material being pushed out with the fill slope. You can see as it's moving left to right, you don't see any preceding raises that would be caused by that soft organic silt. Next slide, please. So this is those same profiles shown from a side view. These are pretty unique because you can actually see the moguls. So you see that they are there, and there's not a preceding mud wave that was shown to happen as this fill was going in. One of the useful pieces of information that we were able to gain from this was when this material is being pushed in, what slope is that material actually falling at? Now this was that geometry problem that Jim had mentioned and would come into play later when we went to sequence that closure wall. Next slide, please. So as the mass fill progressed, the next step was to actually densify the fill. We had to meet those performance requirements, liquefaction, resistance, bearing capacity, settlement. So in order to compact it, we used two methods. The first was vibro replacement with a vibro float. Vibro replacement, as the compaction probes are densifying the soil, additional material is placed at the surface. This material is taken down into the hole with the probes, densified, and makes a more rigid structure. The second method, this would be vibrating pile compaction, also referred to as VPC. Each method had verification test programs. This was done to determine the most efficient spacing and also to determine that the density requirements were being met. And this was all confirmed using test borings and SBT N values. Next slide. So the first method, the vibro replacement, the compaction energy is actually coming from a eccentric rotating motor that's on the tip of the probes. For this project, we actually used a tandem setup, so we were able to actually install two probes at once, and this was actually a first in the United States at the time of the project. For the compaction requirements, this project used 12-foot grid spacings, so the probes were 12 feet apart from each other, and each subsequent location was 12 feet apart from that. And this was used in both the 3,000 PSF and 5,000 PSF loading areas as it met that required compaction. Next slide. So the second method that was utilized, this is that VPC. So the VPC, it works by having a ribbed steel plate that is hydraulically driven with a vibratory hammer. Now, as the probe goes in, all that compaction energy is coming from the vibratory hammer at the top of the pipe. We found in our test programs, we needed two different probe spacings and configurations to meet the required density of the different loading areas. This method was able to compact about 40 locations per workday, but the VPC was really useful in that all the energy and components, they're actually at the top of the hammer. So we were able to drive this and compact areas where fill had been placed over buried riprap slopes, or where the tandem probes would have been more difficult to control, such as between the tie rods when we went to do the closure sequence. Next slide. So the test programs were basically controlled grids where we varied the probe spacing, and we were able to get a representative idea of what each spacing would deliver in terms of compaction results. So by varying the spacing of this is for the vibro replacement, by varying the spacing of the probes, between 10, 12, and 14, we were able to determine that the 12-foot spacing was the most efficient because it met the compaction of both zones based on the borings that were performed after the compaction was completed in these test grids. Next slide. So similarly for the VPC method, we also did a controlled test program. Here we varied the number of drops or how many times the probe is actually inserted into the soil. And we came back and we did the test borings to determine what level of compaction was achieved. And this was used to determine the probe spacing or the drop configurations for the VPC method. Next slide. So the confirmation borings were very useful. We were able to do continuous sampling to get a continuous profile of what the density of the soil was throughout the fill layer. So we performed these both pre and post compaction. So as you can see in that graph on the right, in the gray plots, that's the pre-compaction. So most of those end values are less than the minimum of 10 that was required. We performed the compaction and then we came back and did the test borings, and those are plotted as well. So the orange shows one of the 3,000 PSF area borings where the compaction was raised to over an M value of 10. And then the green shows an area where it was raised to over 17 for the 5,000 PSF area. So there was quite a bit of increase in that density after compaction. And these borings were repeated throughout the basin as required at 33, 66, and 100% completion. Next slide. So as the densification and the mass filling progressed, as you reach the end, we had to start thinking about the closure wall. So the closure wall of the basin was designed as a pipe Z combi wall. You had driven king piles with interlocking sheets in between each of the king piles. And there was tie rods that connected this combi wall to a concrete deadman that was anchored by an A-frame of steel H piles driven to bedrock. Next slide. So one of the main concerns with the subsurface profile here is if we did bury the organics below the fill, you could get excessive settlement where you have already driven H piles. You also had to make sure that the fill was densified. The concern with that was if you had settlement or down drag, these piles could experience internal stresses that might cause bending, deflection, or even breaks in the H piles. So that area was specified to be dredged versus the rest of the basin where the organics were simply left in place. So when we first looked at where this was going to line up, we compared the fill slope of what we had seen in the bathymetric surveys to determine what height that uncompacted fill would raise up on the wall. And this was critical because prior to the installation of the tie rods, there was a maximum height that this fill could rise when the wall was in a cantilevered condition without risking any failure of that combi wall. So based on that geometry, we determined that the deadman actually had to be relocated further back to prevent that loose fill from rising too high on that cantilevered combi wall. So once that location was determined, it was dredged and fill was placed to 20 feet beyond the deadman alignment. And what this distance allowed us to do was actually compact the whole area that the battered H piles would be driven in. So that way we had a compacted zone and no organics, which would limit the risk of settlement in this deadman system. Next slide. So once that deadman system was installed, they were able to place that infill all the way to the end and have a complete filled in central wharf. Once that fill was placed between the deadman and the combi wall, they were able to compact that using the VPC method. And once all this work was completed, they were able to install the finished surface, which was a 3-foot layer of dense graded aggregate that was placed and compacted using conventional earthwork methods. And the finished product is a multi-purpose surface that will allow the staging of these offshore wind components and the operation of cranes and heavy equipment. And one benefit of that dense grade surface is it's easily regraded over time. Next slide. Thank you.
Thanks, Greg. So yeah, with that, I guess we'll wrap up. Like I said, the State Pier complex was substantially completed in the spring of 2023. Since then, they've marshaled components for the South Fork Wind Farm, which is complete, and they're currently marshaling components for the Revolution Wind Farm, which construction for that is ongoing. So yeah, thank you very much.
Awesome. Jim, Greg, thank you very much. That was really informative and, pretty unique and an interesting project. And, I really appreciate you guys sharing, that with our group today. So thank you very much. As we move on to the second half of our webinar series today, we are graced with the presence of Glenn Santulli of GRL Engineers. He's going to be doing a presentation talking about the nearshore and offshore pile driving and high strain dynamic testing that he's performed, looking at predictions, installation, and results. So, Glenn, thank you very much, and I'll turn the presentation over to you.
Thanks, Seth. I'm glad to be here with everyone here today, this afternoon. We'll get started. As Seth mentioned, I'm Glenn Santulli from GRL Engineers, the Philadelphia office. Going to the next slide. Oh, there we go. Okay, just a general outline here of everything we're going to go over today. Some general installation of nearshore piles and jacket piles. Do want to mention this presentation today is going to focus more on nearshore pile driving that might be more closer to the U.S. This presentation is not going to go over Gulf of Mexico or Middle East, deep water offshore. If that's something you're interested in, we can talk to others at GRL about that at a different time. So back to the outline here, we're going to go through some basic design methodology. This is not a design presentation. Challenges and complexities when installing piles offshore, more of like a nearshore environment. We're going to look at some prediction models via GRL WEAP for the nearshore offshore jacket piles. Use of dynamic testing via PDA for the nearshore jacket piles, what that allowed us to do and the benefits. And one takeaway is making field decisions from dynamic testing data in this nearshore offshore construction environment. So just some general thoughts here about the nearshore offshore pile driving. If you're asking, what's the purpose of this? How is this involved? Often for mooring and breasting structures that would have different vessels coming to it. Could be for offshore wind, could be for oil and gas, could be for a bunch of different things. Jacket style structures, which we're going to go over here shortly, are often used with jacket piles for nearshore structures that need to basically remain in the offshore nearshore environment. This is also utilized for lighthouse and light tower foundations that occur in the nearshore / offshore environment as well. So it's just some general pile jacket basics. The two photos in front of us here, the one on the left-hand side is going to be considered our Project A. We're not going to use any names or client names or owner names here in the presentation. And the one on the right-hand side, we're going to call Project B. Both of these are jacket structures. Both of them are more of the nearshore environment, ranging from, a couple thousand feet to 10 to 15 miles offshore. Typically, they're designed on the more push-pull methodology. What I mean by that is if you look at these jackets and you see more of a vessel impacting it, obviously one side would be more in tension, one would be in compression. Obviously, the impacted side would be put into tension and the reaction side would be put into compression. So typically these jackets are based on 4, 6, 8, could be a tripod of 3 piles, and all based on tension and compression loads to give the jacket lateral resistance. They're typically designed to resist boat impact loads. They often typically also have a minimum penetration for lateral stability, but typically you drive well past that to get your axial resistance. So it's not really a major constraint in the field while driving. So a GRL WEAP drivability study, typically in the pre-construction phase, well in advance, and I mean months, if not sometimes years, before we would be going out to actually drive any piles. a lot of drivability studies are typically done. One of the topics is evaluation of your pile order length, which is way different than if it was a typical on-land job where maybe you could call up Nucor or any of the steel manufacturers and just bring in, a couple 100 feet of steel in 3 days. This typically incurs more downtime. The piles need to be barged in. It's a whole different complexity now when dealing with this nearshore / offshore environment. Typically, it's much more expensive. Downtime becomes way more expensive and is significant. And a lot of drivability studies are often done in the pre-construction phase to look at, okay, are we going to get capacity at the design tip? Are we going to get it at initial drive? Do we need to do a restrike? Do we need to better establish our order lengths? The price of steel is going to be much more less expensive than any downtime out there trying to figure it out. As I previously mentioned, we typically in the pre-construction phase doing these drivability studies look at, are you going to need to do a restrike? Sometimes the specifications may require it. If they don't, obviously everyone's going to want to avoid it. So in this case, which might be way different mentality than on-land pile driving, adding another 40, 50 feet of steel is probably way more less expensive than having to do a restrike and put the barge on downtime. Typically, contingency plans are developed early, months before we go to drive piles, to look at, okay, what's our plan A? We get it on initial drive. Plan B, we drive deeper. Plan C, maybe we have to do a restrike, all fully developed well before months in advance ever putting a pile on the ground. One other item that comes about in the nearshore offshore environment, and again, this is on the left-hand side, we're going to further get in depth here, is our project A. Our project B is on the right-hand side, is how the hammer is being supported. And what I mean by that is if the hammer and the leads, or there's no leads, typically offshore you don't use leads, but on the left-hand side you do. If the hammer is supported by the pile, then you can often get bending stresses if it's a battered pile. The right-hand example is a very good example of how bending stresses will be created. So that weight of that hammer, which in this case could be 50,000 pounds, is going to develop a bending moment in that pile until it's closer driven down to the jacket elevation. So one thing when you're looking at an offshore, nearshore pile drivability, how is the hammer being supported? Is the pile supporting it? Or on the left-hand side is an example where it's probably a combination of the crane, the jacket, maybe slightly the pile, I would say, but typically not as significant as the right-hand side. I want to do a little bit of a close-up so everyone can further understand what I'm getting at here. So this close-up here, this is a offshore pile sleeve, where actually I remember that dimension because I've actually walked inside that one, and that's 12 foot 8 inches. So that's 12 feet, actually. The scales might be a little bit off, just looking at it. That sleeve actually goes over the pile. So the pile maintains the hammer, and therefore it develops bending stresses. So then typically in GRO, in the offshore version, you can look at bending stresses and axial stresses, which is typically known as your combined stresses. So now looking at your combined stresses, you might need to adjust how you drive these piles. If this is something that is, let's say, missed in the pre-construction phase, could be pretty catastrophic driving the piles, not considering bending stresses. So anytime we're in a nearshore, offshore type environment, this is something that needs to be considered. So we're going to go over example project A here. Again, we're not going to go into project names or clients or owners or contractors or anything like that. Project A here is, I will say, it's a project in the Delaware River. It is a lighthouse project. Jacket foundations were chosen as the foundations to hold up these lighthouses or light towers. These were 6-leg jackets, which means there's 6 sleeves, essentially, where you would drive piles. Each pile has 1 splice or 2 sections. Just to give you a little bit more of a better understanding of this offshore and nearshore environment that I think I wanted to just relay to everyone here, to see the complexities and the challenges, is, you're required to get a boat launch. Might only come once or twice a day. It's not as easy as driving a pickup truck to a construction site and just coming out and then voila, we're here. This type of work for this project was actually probably, half a mile off land. It was in the middle of the Delaware River, kind of on the state lines of New Jersey and Delaware. Typically classified as nearshore work. That's what the offshore experts would tell you. And the jackets and jacket piles have to all be barged in. I think the bottom section was maybe 125 feet. So typically, you would never mobilize that on land. For this project specifically, we ran several models estimating capacity during initial drive and restrike, with the idea being, obviously, we don't want to be on delay while we're out there. We want to make sure we get capacity. We want to make sure we're ordering and purchasing well exceeding what we need to be on the more conservative side, because the price of steel is much less expensive than barges on downtime. So in this situation, we developed a couple models conservatively, and with, like I said, material cost is much less than barge downtime. I do want to mention one thing. I want to go back real quick. In this specific project, restrikes were not required. So we had the ability to look at different models and say, okay, what if we drove deeper to avoid a restrike? That would be more cost effective than having the barge on downtime for a day or 3 days. So this is that type of situation where you would try to do anything to avoid a restrike. Driving deeper, additional cost of steel, much less expensive than being on downtime for 3 days. So after we go through the drivability analysis and the pre-construction phase, then obviously we're now into the installation phase. So this is just a great photo here to see kind of what you're up against. Obviously not just pulling a pickup truck onto the job. You're going to be taking a boat out. You can see the jacket there with a barge working. The boat typically could range from maybe 30 minutes to several hours for just the nearshore work. Might only come once or twice a day. And I do want to mention, because I think this kind of goes to the environment and challenges, even in the middle of the Delaware River here, we're pretty much on the state line, Delaware and New Jersey up in here in the East Coast, probably not going to have cell phone service there. Internet, non-existent, because no one's going to have internet on a very small size barge in the middle of the Delaware River. And boat launches could be once or twice a day. So if you need to go on land or make a phone call or internet or anything like that, probably not going to happen. So now we're going to get to the dynamic testing phase of Project A here. For these type of projects, sometimes testing for the dynamic testing could be one pile per jacket, or it could be testing every pile at the jacket. As previous mentioned, restrikes could be required, may not. This specific example A, not required, so we would do everything we can to avoid restrikes. And due to the nature of the offshore work, the contractor typically only wants to lift the hammer one time. So that means they'll splice all the piles, they'll lift the hammer one time, they'll drive the 6 top sections, and that's it. The hammer's put down, never lifted again for this project until we go to the next location. For this example, also bottom sections were installed with a vibratory hammer. A little continuation here, the dynamic testing. For this specific project, one pile per jacket was tested via PDA. As mentioned, bottom sections of the vibratory hammer were approved by the engineer and contractor. Sometimes using a vibratory hammer to install jacket piles is not allowed. There has been studies that you will reduce the amount of friction developed long-term or even during driving, but in this case, we were allowed to use a vibratory hammer to install the bottom section. So one top section per jacket location will be tested via PDA. And kind of want to go over kind of what I mentioned before is the plan was we test one top section and then immediately provide the results, because in this case, the hammer is only going to be lifted up one time. It's going to be then brought to the other piles, and then the project's essentially done. Now, that's why I mentioned before, with no limited cell phone service, no internet, nothing like that, it's really important in this case, whoever's doing the dynamic testing has to be, fully competent, obviously well experienced, but be able to provide results immediately. By immediately, I mean When that hammer is done, the criteria is developed for the next one, which will probably that hammer we put on in the next 10 minutes. So there's no time of, oh, let's call the office and let's look at the data. No, it needs to be done immediately because the barges cannot be delayed whatsoever. And you don't even have cell phone service or internet to even send any data. So this is a whole different ball game. I'm sure plenty of people here said, oh yeah, I've been out for dynamic testing all the time. Person out there just calls the office. They go, not going to fly in this situation. So just some conclusions here about Project A, if there's anything takeaways. This is a project in the Delaware River, nearshore pile jackets. The drivability study was used to modify and adjust pile lengths. We went conservative, just speaking with the contractor, just to avoid downtime, make it more cost effective, even spending a little bit extra money on steel. Contingency ideas and lengths were built in to avoid restrikes, to limit downtime as well. Dynamic testing was utilized to test the first jacket pile and then provide driving criteria for the remaining 5 without even ever putting the hammer down. So immediately using results right then and there in the field. And then that's pretty much it for Project A. Now we're going to move to Project B. This is going to be, again, we're not going to say any specific names, engineers, or clients, but I will say it's an LNG offshore terminal in the Caribbean Sea. This one's a little bit more offshore, although the offshore experts, I'm sure in the Gulf of Mexico, would still say this is a nearshore job. Again, these were 6-lead jackets for vessel mooring and breasting structures for liquid natural gas. GRL weep drivability studies were performed. Dynamic testing was required 1 pile per jacket. And then 72-hour restrikes to kind of give you the flip side here. 72-hour restrikes were required on all the test piles or all the piles with high strain dynamic testing. So generally cohesive soils per the contract documents, mostly cohesive, I'd say, maybe some granular, but ordering longer piles was not really an option. The piles were ordered, unfortunately, years in advance. So we weren't able to say, hey, what if we look at longer piles or anything like that? It was estimated to have around 50% of the compressive capacity on initial drive, meaning that the additional 50% was assumed to happen during restrike. So the ability to avoid a restrike wasn't as easy as I'd say everyone wanted to. And to give a little other perspective here, this project was about 15 miles offshore where everyone was living on an installation vessel, which means this is operating 24/7, extremely more expensive, probably has a crew of 100 to 200 people living on the vessel. There's no boat runs every day. This is a very expensive operation for standby. So as mentioned previously, the distance offshore, working 24/7. The water in this location was too deep for spud barges or smaller barges. It's not cost effective with the price of fuel to be boating crews back and forth every day. So everyone lives here on the vessel. Add some complexity on the testing and pile driving because it could be at 3 a.m., could be at 9 p.m. It's a 24-hour operation now. As you can tell, pile driving is going on at nighttime. So we're going to continue here and go through some of the project details. Here's a picture of actually testing one of the piles. I actually took this on a kind of a little makeshift table. As you can see, barely see land. This is one of the jackets here, 6-leg jackets. And the idea was we would monitor the entire initial drive on the first splice section of each jacket. So obviously we're not monitoring the bottom section. Vibratory hammer in this case, because the engineers thought it would reduce the amount of friction we would get on a restrike, was not allowed. So, but the bottom sections were impact driven, but we didn't need to monitor. So we monitor just the second piece or first splice section, 1 pile per jacket. Several main cables had to be used because you have to run them through the barge and from the jacket, things like that. And the idea was we would, test the first initial pile, run cap-up analysis on it, estimate the total number of percentage of total capacity we have compared to what is required. And then obviously 72 hours later, we would come back, restrike it, and hopefully be above what the required is. So typically how the schedule events would go down we would test the first pile per jacket to kind of start that 72-hour clock. Then the contractor would drive the other 5 remaining piles. Problem with this specific job that we kind of was always a conversation piece, it would take the contractor maybe 24 hours to 36, that's continuous throughout the day and night, to drive the other 5 piles. So this would leave us with maybe 48 hours, 36, I'm going to say in that range of standby, where basically you have an offshore vessel just sitting there, no work being performed. Sometimes these run up to $1 million a day operating cost. So you can see now the cost of the downtime going on here. Of course, everyone's asking, how do we avoid this restrike? How do we avoid this downtime event with everything going on? Obviously, then we'd eventually restrike it after 72 hours. We'd run the cap lab, give it to the engineer who was on board, and they would decide, okay, did we meet the capacity or not? From the initial drive and restrike data, we would compute setup factors. Typically on this project, setup factors range between 2.5 and 3, and that was only on friction. We didn't see much setup or any real end bearing gain, which is pretty typical in cohesive soil, especially in an offshore type environment. So we're seeing the friction go, well over double, if not triple, in 72 hours. As expected, after 3, 4, 5 of these jackets, everyone's asking, $1 million a day operating cost. How do we kind of get away from this? And this is a discussion, obviously, with the engineer of record and everything, comfortability, and that's part of the conclusions here. So considering the proximity of each jacket to each other, and this photo really shows how close these structures are all together. I think this one we were driving piles, maybe on the 4th jacket, but there might be one behind it. I can't remember, but at least 4th or 5th one, and they're very close to each other. We were getting setup factors between 2.5 and 3. I think the minimum I looked up was about 2.45, and things were pretty much in line, where we started to have the conversation of, what if we look at initial drive? And if we think a conservative approach that we're going to get maybe half the capacity we need, when we know we're getting between 2.5 and 3 on the setup factor on the restrike, do we have enough confidence to maybe avoid it? And that was kind of the thought that was thrown around. We talked about it with the geotech engineer, and that ended up the direction we would go for the last couple of jackets. So this would now turn into, you test the first jacket pile, we look at what's going on, we would do basically the back calculation. Now, what setup factor is required to get capacity on a restrike? And if it's, coming in slightly below what we saw in the last 5 or 6 jackets, then the engineer was able to say, okay, well, maybe we can rely on the other data we have in the area and kind of forecast out the setup factor, which obviously leads to a more cost-effective installation process. So just some conclusions here about Project B that I wanted some takeaways for everyone here to kind of digest on a little bit. Dynamic testing was performed on 1 jacket pile for each of the jacket structures, this project being in the Caribbean Sea LNG project. First half of the project kind of went according to specifications, I'll say. Dynamic testing was performed on the initial drive of 1 pile per jacket. We did the 72-hour restrike. We evaluated the setup factors. Due to standby costs and downtime, obviously the idea was, how do we make this more cost effective? How do we avoid downtime for a 200-person vessel just sitting idle doing nothing? And what's it called? And then basically the next step was, all right, we're going to back calculate what the required setup factor would need to be in order to avoid the restrike, to try to be more cost effective. And I guess something I thought I would share with everyone else, someone on a different project put this kind of thought in my head a few years ago that kind of made me think about it different. I'm sure there could be people in the audience say, well, what's this guy talking about? You just do the restrike. Who cares? It's downtime. Something like a 72-hour restrike, hypothetically, because you're in the offshore environment, you're not on land anymore. What if 2 days later you get bad weather in? And now, in this type of environment, you got to move your barge, or you got to move your vessel back to land. And maybe it's similar to a hurricane. Maybe it's not that bad. 2 days later, now we got to go back to land. We got to wait, have to wrap up everything. Maybe you wait back to land for 2, 3 days, go back to the project location, get everything back up and running, reset out anchors. That could be a day. Or if you're using spud barges, you're going to have to put your spuds back out, things like that. If it's an anchor vessel, it's going to take a little bit more time. If you're in that situation, that could delay the project maybe 7 to 10 days if something like that happened, where maybe you didn't have that restrike, you didn't have to wait 3 days. You would have already wrapped up that location, finished it, done, went to the new location. Yeah, maybe you still have the weather downtime event, but that location's done. You don't even have to go back to that one. Now you're going to set up maybe a shelter area for weather. Then you go back to your next location. And you might have picked up close to a week just in moving back and forth, setting up. So sometimes a 3-day restrike could expedite much further just due to other environmental effects. So just something that a perspective, someone put that in my head a few years ago, I thought I would share. So one other topic here, I know which was listed in the DFI letter that went out, would be other dynamic testing possibilities. What else can we do? We've mainly focused on jacket structures, but what else can we do for the dynamic testing in the nearshore offshore environment? And the other industry is the offshore wind environment. Typically offshore wind structures for the turbines, most of the time have jacket style or monopile foundations. Monopiles are typically, from what I've heard, I'm not the expert in this, the preferred option. The reason is to limit the amount of steel. With a jacket structure, there's just so much more required steel because you have the jacket itself, you have the 4, 6, or 8 piles you have to drive compared to one monopile. The limitation, from what I've heard, is typically though the water depth. When you get over a specific water depth, the monopile doesn't have the lateral resistance anymore. Now you have to go with a jacket foundation. The ballpark number I've heard, again, not an expert, is somewhere around 50-meter water depth. And then let's go to the next slide here. This is just a little chart to show you a jacket, a monopile, and then like a gravity or suction pile, as they call it. So some general things about a monopile here. That is a photo of myself just to show you the scale of how big they are. Significantly bigger than anything you typically driving, on land or even a jacket pile. Typically designed on lateral loads. We're looking at lateral stiffness of the soil. Not very concerned with axial capacity, not like a jacket pile, which uses the push-pull methodology. Two main design parameters are typically the lateral stiffness or lateral resistance of the soil. What I've heard from conferences and seminars is for a monopile, they actually talk about an ultimate resistance for lateral, which is typically D/10, where I know you talk to some geotechnical engineers, could be on this call right now, where they say there is no lateral resistance for a lateral load or a lateral resistance during a lateral load test. It's not like a compression or retention. Typically, a design parameter is you limit the displacement or the deflection to D/10, and that's considered your ultimate resistance. So the other design parameters, can you get this pile to the required depth in order to meet your lateral resistance? Just some more monopile basics. Unlike jacket piles, which typically if you refuse early, you can look at it. If you're fortunate enough to have any PDA on board, you can look at what the axial tension and compression capacity. So if your jacket piles refuse a little bit earlier, you might still have your tension or your compression capacity. Typically, a jacket pile, if it refuses early, would be rejected, or further engineering evaluation is going to need to be done. Can we still use this for the lateral resistance? Substantial research is going on in the industry, and probably I'd say any geotech engineers on the monopile side of offshore wind, not the port side, or I know this is focused on ports and things like that, but on the monopile side, that is the biggest question mark. That's what everyone wants to know, is predicting monopile refusal. When it's going to happen, is it going to happen early? Because the significance and the cost of if this happens early, you could lose the whole turbine. So that's where all the research, that's where everyone wants to talk about for the monopile side is, are these going to refuse early? What's the drivability like? How long is it going to take? What hammer size do you need? On an effort in developing more reliable drivability studies, one thing that we're currently doing, and it's currently going on in the industry, is collecting dynamic monitoring data there and basically compare it to your original drivability studies to refine your model. So it's almost looking at dynamic testing from a different light to refine your geo model, not necessarily look at axial capacity, but what's your soil distribution, what's your resistance, what's your friction at this depth, what's your end bearing at this depth. The assumptions we made that we can install this pile to this depth, are they still accurate? Is that still a good prediction model? So that's currently what's going on. And that's really where the future of the offshore wind, I'd say, and offshore industry is. It's refining models by use of dynamic testing. So just a little example, I guess, kind of to conclude everything here, the monopile offshore wind industry. To better aid the offshore wind industry, obviously GeoWeek can be utilized to develop prediction models, assist with hammer selection, feasibility. However, everything's still a prediction model. How reliable is that? And everyone has a million different opinions on that topic itself. And dynamic testing and monitoring could be utilized to collect real data during driving to better refine that model. Obviously, actual soil resistance during driving could be much different than anticipated, as we see on land or we see anywhere. And then comparisons can be done from the original prediction model to modify or adjust the next model. And obviously the goal being to avoid early monopile refusal. Thought I would just show this, roughly a monopile hammer. I did take that photo, although it's at an undisclosed location and project name. And due to the current size and water depth of most of the proposed turbines, actually all on the East Coast, they have had discussions of up to 12 meter plus in diameter, maybe even bigger. And the current engineering on the hammer selection, the hammers aren't even engineered yet to drive the pile. So actually the pile size is further advanced than the engineering needed to drive them. It's currently what's going on with these monster size monopiles here. So just thought I would give that as a reference here. That is, or as of 6 months ago, was the second biggest hammer in the world, slightly by like 1 kilonewton, kilojoule short of, everyone has to be neck and neck as the biggest hammer in the world. And that's pretty much it. I guess any questions? I don't know if we're opening it up to everybody here.
Glenn, thank you so much. So yeah, what we're going to do, Glenn, is we're going to hop into the chat and see what questions have been asked for the various speakers, and hopefully, whatever additional clarity we can offer, and answer the questions. But that was great. But Glenn, thank you so much. That's some really excellent information. Really, interesting topic, and as someone who's done a lot of PDA myself over the years, it's always impressive to see, the applications and the types of solutions that can be provided through dynamic testing. So pretty awesome stuff. But yeah, with that said, I guess let's go to the chat and see what questions we have. So, I guess I'll start with the second question first, Greg or Glenn, just because you're here. And it's more of, I guess, maybe a theoretical question. And what is the need for the restrike, presumably on the piles we're talking about, and what is the theory behind performing the restrike?
Well, the restrike, I guess, just kind of basic to go over some basics would be if you don't get the capacity you need on initial drive, you would do a restrike to look at after driving, typically known as soil setup, where is essentially the pore water pressure dissipates, and you're looking at more the long-term capacity. So I guess to simplify it, maybe you need 600 kips in resistance, you got 300 kips on initial drives. The question comes, do we splice another section, drive deeper? Or what do we do? Some jobs are specified where you got to do the restrike because the design methodology is based on that long-term capacity during the restrike. Or if you're looking at more project A, during the drivability phase, you could see, hey, maybe at this depth you're getting it, or at a capacity at restrike. If you go deeper, you could get it at initial drive. What's that difference? Okay, it's 30 feet. What's the cost of 30 feet of steel? I hope that answers the question.
Sure. No, I think that's a good answer. Stick with you, Glenn. There's a question. Why does a monopile have such a tendency to refuse early?
I don't necessarily know if it's a tendency. I would just say more if it's a risk, because you need the lateral resistance. So if it refuses early, can you still use it? I don't know. I don't think tendency, I would say, is a correct word there. I'd say risk. It's a word.
Okay. Excellent. I'm gonna switch gears a little bit and address the next couple to Jim and Greg. Looking back at your presentation, Jim and Greg, it says in the graph between the N value and depth, N values are varied a lot with depth after densification. What could be the reason for the high variation?
That's a great question. So with the densification, we believe that there was a lot of excess pore pressure that was developed. We actually waited 2 weeks between the time of densification and the time of drilling to let those pore pressures dissipate. So there could have been some residual still on the ground there. The specifications on the fill material, it was actually 12-inch minus. So every once in a while there was a boulder here and there. The material sources, it was a natural gravel pit from a sand and gravel pit. So yeah, I think it's just the as the probe was going down, there could have been zones that were densified a little bit more than others, because I think for the most part what we saw was a lot of spikes. We'd have generally blow counts maybe in the 15 to 20 blows per foot range, and then there'd be a spike or a layer where it was 40 to 100 blows per foot kind of thing. So I guess to answer your question, I don't have a good explanation of it, but I'm assuming it has to do with the amount of oversized material in the fill and possibly some excess pore pressure.
Awesome. Thanks, Jim. Another question here. How did you estimate the negative friction on the piles in the wharf fill?
Is that directed to us?
I guess I'm not sure. That maybe that's for Glenn then. I'm not sure. It says it's from Rick Evans. How did you estimate the negative friction on the piles in the wharf fill?
Or maybe he's talking about the dead man piles.
Yeah.
So that actually wasn't designed by GZA. That wasn't part of our scope. That was designed based on a specification of the material type. So I think it was just a frictional pile calculation, but based on an anticipated material, anticipated density, and then all those piles were tested.
Yes, I can tell you, we actually worked on the testing, and
right.
that's a whole nother presentation, Jim.
Yes.
Excellent. And then Glenn, another one for you. Do the project owners / owner's engineer specify how setup is evaluated, in particular for tension capacity? Is this taken from CapWAP outputs? Question mark. Are there any reductions applied to this?
Yeah, it's an excellent question. Typically, yes, it is taken from CapWAP. Often the industry practice is to remove the bottom element of the CapWAP. There's, depending on the situation, but the conservative approach would be remove the bottom element and then take 80% of the friction for the post-on effect. That's typically the industry standard. That's also applied in the offshore environment as well.
Okay. Excellent. Well, I will give the audience one last chance. If you have any additional questions while we have these experts on the line, please chime in on the chat. We do have a couple of more minutes here on our webinar before we sign off. So there's definitely time if anyone's thought of something else. But in the meantime, I'm gonna give you a little bit of a look ahead to 2025. So as I said at the beginning, we're going to continue this webinar series as we move into 2025. Right now we have 3 events scheduled, one in March, one in July, and one again next November. And as of the moment, we are actively looking for participants, folks who want to share their experiences in the driven pile industry for each and all of those dates that we have coming up in 2025. So I highly recommend, if you have something to share, this is a great forum to do that. It's a great opportunity to kind of spread the type of things you've been working on. Again, we're looking for all types of different projects and different ideas related to deep foundations and specifically driven piles. Yeah, it's definitely wide open for anyone that wants to contribute. You can reach out to me or Travis Coleman or Greg Canavan, the 3 folks who sort of make up the leadership of the Driven Pile Committee, and we can get you tuned up. I also would appreciate it if you took the time to log into this webinar. If you're not a member of our committee, I would highly recommend that you join. We meet on almost a bi-monthly basis online, and we're really looking to try to ramp up activity in 2025, and so we would appreciate all of your contributions. And yeah, there are no other questions. So as a follow-up, we're hopeful that you paid to obtain the PDH certificates for today. Again, it's a relatively cheap price for a PDH certificate in our current marketplace, and so we really think there's a lot of value associated with doing that. So if you did pay, there'll be an evaluation that you will have to fill out, and then once you do that, you will get your PDH certificate. DFI has really made a big push to embrace webinars as a way to kind of connect with our membership more regularly than the in-person events that we do. So please check out the website. You'll find webinars on just about every topic across the spectrum of DFI and the various committees that exist. And we also appreciate your feedback and suggestions on how to improve as we get better and move forward into next year. And you can always direct any specific questions to the website on the screen. And so with that, I really do appreciate everyone joining us today and giving these folks your attention. Glenn, Greg, Jim, thank you so much for being a part of this and helping push our committee forward, and we appreciate it greatly. Thank you.
Thank you.
Thanks.
Thank you, everybody.
And yeah, I guess with that, we will conclude this edition of Impact, and we hope to see you again in March as we explore another topic related to Driven Pile Foundation. So thank you very much, and enjoy the rest of your day.
Thank you.
Thank you.